Okay, hi linear algebra, how are you? I am not in today, obviously, but you have, I think you have Miss Szlapleski in class with you right now. So what we're going to do today is we're going to go over homework from the weekend and let's do this. Let's hold off on the hard due date for the take home tomorrow. Let's negotiate the quiz that we have planned this week. Maybe we'll turn it into like an overnight take home overnight quiz. Okay, so let's just take that off of our worrying back burner if that's there, and let's just try and understand the homework from last night. Let's go over every single question here, and and then what I'm going to have you do is work together on the homework that I will post on the calendar, and you may already have seen that. Okay, so the first one, 24, and I did the harder of the two. I did 24b. I think this question was asking you here to show that this transformation right here is not a linear transformation. If it's not a linear transformation, what we have to do is show that it fails one of the two required properties, the scalar multiplication property preservation and the additive property preservation. And when you're proving something is not a linear transformation, all you need to do is disprove one, and the game is over, so to speak. Okay, so here I am testing scalar multiplication, and the question really is, does the transformation applied to k times an input equal k times the transformation applied to an input? And remember, in class, I said that in its general form, the input is referred to as a vector. And in this case here, if we look at this transformation, some of you are kind of just telling yourselves to think of this as a vector in 3 space with the 3 components. That's perfectly fine. You can also think of this as just an ordered triple. So it's important to just kind of to then just make the switch and make sense of what this thing means in context. So in this transformation, k times vector u means k times an input, okay? And then similarly, k times the transformation applied to u equals k times the transformation applied to the ordered triple. All right. Now, all I do here is just the algebra, and I think we're kind of squarely in the place where we see that even though this course doesn't go really much beyond addition, subtraction, multiplication, we find ourselves in pretty abstract territory pretty quickly. Okay, so k times u, when I distribute the k, it becomes the transformation applied to the transformation applied to k times x1, k times x2, k times x3. And this transformation says that the output or the image of the x coordinate of the image is exactly the same as the x coordinate of the pre-image. The same goes for the quote unquote y coordinate or the third coordinate. The only change is that the third component, the image, is the square root of the pre-image. So that's where things are a little bit anomalous. Now, if we look at that here and I apply that transformation rule, where I am is right here. Okay. If I ask myself, well, does this t times the transformation applied to k times u, does it equal k times the transformation of u? Well, let's see. Let's do it out. So here you'll notice that what I need to first apply is the transformation applied to x1, x2, x3, and I know that that output is right here. And then k times that, I didn't write it out, but it's going to, at the end, equal kx1, comma, kx2, comma, k root of x sub 3, okay? And these are not equivalent. These expressions are not equivalent precisely because of this third component here, okay? All right, so we have shown that the transformation defined as such is not a linear transformation. Okay, 26 was a bit, there's a lot going on here just in terms of the words. I don't think that the actual work itself was difficult, but the words make a difference. And you might want to have your text or something out. I'm looking at the text right now. The words say that show that the transformation xy that yield 0, 0. It says defines a matrix operator. What I'm going to do is have you do this, okay? I'm going to say show that the transformation xy equals 0 defines a, let's just call it a matrix transformation, okay? That's what your text meant. That's what your text meant. I'll go into this at the end of the question here, but when you're showing that a transformation defines a matrix operator, what you are then doing is setting up yourself to write the matrix transformation as a matrix equation where A is the transformation matrix. We'll get to that in a second. So the task at hand is to show that this transformation right here defines a matrix transformation. And the way you do that is just like what you've done with linear transformations. We're going to go and show that this transformation is a linear transformation. Remember, all matrix transformations are linear transformations, okay? Now, when I do this proof down here, okay, all of this is just proving that my transformation is a linear transformation. I am then going to say that given this linear transformation, I can express it as a matrix transformation. So there's two parts here, and we'll do them both. Okay, so the part about the linear transformation. So here I am showing that the transformation applied to u plus v equals the transformation applied to u plus the transformation applied to v. Okay, now notice what you did here. All right, when you are looking at the transformation applied to point plus point, and even if you want to insert a step in here, and some of you may want to do that, you may have said that the step in here, if I were to simplify one step further, it becomes the transformation applied to x1 plus x2 comma y1 plus y2, because that is the result of adding one vector or ordered pair to another vector or ordered pair, okay? Well, the rule of this transformation says whatever the ordered pair is in the parenthesis, the image is always going to be 0, 0. So this ordered pair has this as the x coordinate, this as the y coordinate. The output is 0, 0. Okay, well, let's take a look at the transformation applied to u plus the transformation applied to v. Once again, the output is 0, 0 for both, and then when you add it is 0, 0. The fact of the matter is that these two are equivalent. Let's try the scalar multiplication property. The scalar multiplication property, if I'm looking at the transformation applied to k times u, and you'll see I distributed the k here to the two components, according to the rule, the transformation is 0, 0. K times the transformation applied to x1, y1 becomes k times 0, 0, which equals 0, 0, and these are equivalent, okay? What I've shown here, is that this transformation is a linear transformation. I have not shown yet that it is also a matrix transformation. Remember, all matrix transformations are linear transformations, but not all linear transformations are matrix transformations. A matrix transformation is a transformation that could be expressed like this. So I'm going to do a little recall. Ignore what's up here for a second. So recall. Okay, a matrix transformation can be written as this matrix equation. And you'll remember what we said here is that when you have a matrix equation, what's in here, what's in the X matrix is the input vector that exists in the domain. And B here is the output vector, which exists in the codomain. And we already know that in this case, the input, whoops, pardon me, oh my goodness. That's wrong. The input is always just sum x1, x2, Okay, it's some vector with two components. And the output vector is 0, 0. If this linear transformation, right here, if this linear transformation is also a matrix transformation, there needs to be a way I can express this transformation as a matrix equation and refer to the transformation as this matrix transformation. So this matrix is, we know it's going to be a 2 by 2. So the question is, how do I show this transformation as a matrix transformation? And more specifically, what is the matrix transformation, the transformation matrix, right? Because A is the transformation matrix. Well, you can do, it's not really guess and check, but you probably see what the only possibility is. This is the only possibility. Okay, so right here is where I want to just take a pause for a second, and let's just kind of pull two seemingly, maybe even three seemingly disconnected threads together. If a matrix transformation, let's start over. A matrix transformation, let's start over again. If a transformation is linear, it preserves these two properties, addition and scalar multiplication. If that linear transformation is then a matrix transformation, it can be written in this form with a matrix transformation identified. If a matrix transformation also, if you switch lenses, describes a linear system, we are then able to determine the solution space of that linear system. So that's kind of the thread that links these three seemingly disparate ideas: linear systems, matrices, matrix equations, and then now matrix transformations in the context of linear transformations. Okay, I believe part 2 of the question was this one, is to look at this transformation, the transformation on the ordered pair XY, giving you 1, 1. And I just did the scalar multiplication property because right away I just saw these were not equivalent. So let's talk about the result here. This transformation is not a linear transformation, okay? It's also obviously not a matrix transformation. Right? If it's not a linear transformation, it can't be a matrix transformation. This transformation then, it's also impossible to describe this transformation as a matrix equation. In other words, it is impossible to generate the matrix A that would yield this output. Okay? If a transformation isn't linear, you're not going to be able to express it as a matrix equation. And my other class actually sat here and tried to wheedle around with this. There are no numbers you can input in here to make this statement true, which is kind of a fun idea. Okay? All right, finally, question number 29, it was here. So the green, or the citron, was given to you. This kind of like a persimmon leaf color. It told you the transformation applied to 1, 0 is AB, and the transformation applied to 0, 1 is CD. And I want to look at the wording here. Yes, and they used the phrase here, they said these are linear operators, okay? Again, they're using the word operator in lieu of transformation, which is fine. It's just it's synonymous, means the same thing. They're telling you this transformation is a linear transformation. And if it's a linear transformation, you know that it has to obey both of those properties. And I think it asks you to go ahead and find this, correct? All right. Well, I just did this. The transformation applied to 1, 1. How can I get that? Well, I know that the addition property has to be preserved. So the addition property, the transformation applied to 1, 0 plus 0, 1, has to equal the transformation applied to 1, 0 plus the transformation applied to 0, 1. Okay? And I know these two transformations, the results or the images, it will just be, if I wanted to add a step, it will be A, B plus C, D, which at the end of the day equals A plus C, comma, B plus D. All right. So that is homework for tonight. I'm not going to do any new content. What I am going to give you is another night of homework on this matrix transformation, linear transformation kind of proof content. And I'll post that for you to work on. You can start working on it now together in class. Do work together. I will see you tomorrow. And like I said, go ahead and if you want to pull out the take home, I'm not going to make it due tomorrow, but go ahead and pull that out as well after you do the homework today in class and see how far you can get with that. And like I said, when I see you tomorrow, let's talk about a reasonable and stress-free way to have the quiz this week. And if we have to do it as a take home with open notes, we can certainly do that. All right, everyone. Talk to you later and have a wonderful last Monday of school in the year 2019. Goodbye.